Hello, everybody, and thanks for joining us here today for the webinar on passive acoustic monitoring. We are Heffring Engineering, and we're producing an autonomous vehicle called an ocean glider. This vehicle swims through the ocean by changing its buoyancy. It carries various sensors to observe subsea properties important to science and operations. For example, temperature, salinity, fish populations, or listening for marine life or other vehicles. Some current applications for this data include navies for battle space awareness, data used by climate scientists and oceanographic modelers, weather predictions such as hurricane intensity, fish stock assessments, and marine mammal monitoring. So shortly after beginning this project, we found that passive acoustic monitoring was an area we could provide a lot of value with respect to reducing complexity of operations, reducing total cost of use and ownership of the measurement platform, and scaling up the spread of data that can be made available. Passive acoustic monitoring, as many of you know, serves many functions, including baseline environmental assessments for ocean construction projects, ongoing monitoring for sensitive marine life, and defense applications. Gliders are just one platform for PAM measurements. As we get ready to deliver our first PAM glider in the coming months, we thought operational users could benefit from a tutorial in how PAM measurements, regardless of the platform from which they are taken, work and how to ensure quality data. So we invited our PAM subject matter expert, Chris Jones, to give this webinar. His presentation will be about 30 minutes, and then we'll take questions. To ask a question, please either raise your hand and we will call on you and unmute you, or you can place your question in the chat window and we'll read it aloud. If you would like to ask a question anonymously from the audience, please type it in the chat and send it only to the host. We'll read it aloud when without sharing your name. So Chris Jones holds a PhD in electrical engineering and acoustics, along with a master's in robotics and AI. He spent over 20 years at the University of Washington Applied Physics Lab as a principal investigator in ocean acoustics. He has also worked with the Naval Research Laboratory in Washington, D.C. on AUVs for acoustic measurements and marine science. And he's also built imaging sonars for Blueview. Most recently, 8 years ago, he began consulting on development for passive acoustic monitoring systems. Chris will take us through the scientific principles behind passive acoustic monitoring, and then he'll move on to platform-specific considerations and how to ensure quality PAM data collection. So without further ado, I will hand it over to Chris.
My name is Chris Jones, and I'll be talking about passive acoustic monitoring today in the ocean. So what is PAM, or passive acoustic monitoring? Basically, at the simplest level, it's recording and analyzing sounds of interest with a sensor, and the sensor in our case is a hydrophone. That will be our PAM system. It's called passive acoustics because it's not active. Essentially, active systems are sonars. Common applications of PAM in the ocean are bioacoustics, marine mammal studies and fishery studies. Oceanographers use acoustics to measure things like wind and rain in the open ocean. Seismologists measure earthquakes and localization of earthquakes, and of course, monitoring ships. Noise is a common application for PAM. So what's your experience level? And I think Frida's going to give a little survey here, and then I'll give it a few seconds to get the results on that.
Okay. Here we go.
Is my audio okay, Frida?
Yes, loud and clear.
Right.
So you all should see the poll on your screen. So go ahead and take a moment to answer, and we'll share the results.
Well, that's good. So it looks like some people have built systems. Mostly it's users of PAM systems, so they analyze data.
Okay, looks like most people who want to answer have answered. So we'll go ahead and share the results.
It's a fairly technical audience, which is good. And they're basically users, so you try to interpret the data that you record, which is good because I'll talk a lot about that. Okay. We ready to move on, Frida?
Yes, go for it.
So the outline of my talk, what am I going to talk about today? Well, first I'll give an overview of passive acoustics. I'll talk about generally the physics of sound in the ocean and give some diagrams like this that kind of will help explain this. I'll talk about the passive sonar equation. And I'll do this all because a little physics can go a long way in interpreting the results. And it looks like people here are mostly analyzing data, but it'll give some insights into how you can analyze data and how to design systems. And then I'll give an overview of kind of current PAM systems that people are using at the moment. I'll talk about components of a system. I can show little pictures like this. And then I'll run through some examples of how current PAM systems are used in the ocean. And then we'll end by kind of some thoughts on looking ahead to where we think PAM is going, where we'd like PAM to go. And I'll give my thoughts on what an ideal PAM system could look like. Pardon me. So the best way to start a PAM talk is to start with an example. And this is a spectrogram of some orcas in a passing ship. And I'll play the audio for you. A little heads up on the audio. It gets kind of loud towards the end there, so you might want to have your fingers on the volume button. And I'll talk this through as it's playing. So let's just start this. So those are orca calls, and they're coming loud and clear through against the noise background. Beautiful recordings. I'll try to follow along here. Clicks, you can see following. More calls, beautiful calls. And the ship is coming. You can't really hear it yet. And here's the ship. And it gets louder and louder. You still hear calls, but barely. And eventually it just drowns out everything. It's a crazy, sorry. It's a crazy example because, but it's a really good one to exemplify this concept of signal and noise ratio. And essentially, signal is the sound of interest, and the signal noise ratio is the difference between the sound that you're interested in and everything else in the environment, all the noise in the environment. So if you're interested in whales, for example, these orca whales, in this part of the recording is really good signal and noise. You can see it show up in the spectrogram. In this part is really bad signal and noise against this really loud, noisy background. If you're interested in ships, it's the opposite. On the first part of the recording, you can barely hear the ship, and even though it's probably very close, and so the signal noise is very bad. And when the ship comes in, the noise in this case would be the whales. The ship is very high signal noise relative to the whales. So I'll introduce, so how do you deal with data like this? How do you interpret in a recording like that? Well, the passive sonar equation is a great way to start, think about these things. And I'll introduce this equation with a simple schematic. So suppose you have a source in the ocean out at some distance from your receiver. And the receiver is our PAM system. And the sound propagates from the source to the receiver. The sound has a source level in dB, which we'll call SL. And it propagates through the environment, and it loses energy as it propagates. And the loss of energy, the signal level, is called transmission loss. We'll represent this by TL. And then you record it at the receiver, but you're also recording everything else, like the loud ship, for example. And this total noise level at the receiver in dB called NL. So the sonar equation basically says that the signal noise ratio of your signal of interest is the source level of your signal of interest minus the transmission loss minus the total noise. So why do you think about this? Well, it tells you what to expect in your data, and you can interpret your data in a quantitative sense. It also can give you really good insights into when you're designing a system, where to place the system, what frequency you care about. So I'll talk a little bit about transmission loss in the ocean. And again, this will all be brief, just as background. So the oceans are a really good place for sound transmission. It's because this little schematic will show that. It's because sound travels far in the ocean because it gets trapped in the ocean waveguide. And essentially this schematic shows a sound source, and these are rays emanating out. And the sound bounces off the sea surface and then reflects off the sea floor and gets trapped in this waveguide as it propagates through the waveguide. So that's good because there are simple approximations that can be used to estimate and give you a number on transmission loss. And the most simple of these is what's called spherical spreading. And this little example here gives an idea of what would happen to sound, the geometry of sound as it spreads from a source out in range along the waveguide. And it's called spherical spreading because it spreads like a cylinder. And if you can make this approximation, which you often can, you can estimate the transmission loss to be simply proportional to the log of the range between your source and your receiver. That's a very useful, simple approximation for transmission loss. But in typical shallow water environments, this can get much more complicated. And this is an example of a numerical simulation of propagation loss through an environment or an ocean environment where there's some topography and there's roughness on the surface. This plot shows a source here at the origin, and the colors are basically the essentially the inverse of the transmission loss. So it's the signal level. So the red is high and going down the green and blue is low. And not everyone's going to be able to do modeling like this, but there's a whole cottage industry out there and people that can do this for you if you are really trying to interpret results in a complicated environment. So modeling can give you estimates of transmission loss. And it can also help you choose the depth and location of your sensors. You don't want to be sitting behind a seamount. And recall this as an example. Just recall the orcas and the ships. And so this simulation actually happens to be in the same location that recording was taken, which is the Harrow Straits of the Puget Sound West. And there's a lot of topography there. So suppose that they were recording this at this location, kind of hidden in this depth, which would be a typical place to deploy the PAM system. And as the ship is coming through, even though it's relatively close, 3 kilometers away, you're not really getting a lot of transmission loss. You're not really hearing the ship, and you only hear the ship until it comes overhead, comes by. So that could be what's going on in that recording. So that's how simulations can really aid you in interpreting your data. So you can't really talk about the sound channel without talking about the SOFAR channel, and this is really a deep water, low frequency concept that helps out for a really long range transmission. And the SOFAR channel is caused by this sound speed profile, this inversion in the sound speed as a function of depth. Basically what this causes is trapping the sound in what's called the SOFAR channel. So if you put a source of sound in this channel, it'll never break outside of these this channel, whereas this is the surface and the seafloor. So it won't bounce off the seafloor or the sea surface and lose energy, and it gets trapped in this waveguide and it can propagate for really long. And this is why people use sound to make measurements in the ocean, because it's a really good thing to do. It travels long distances, cover lots of territory. So that's just a brief overview of transmission loss, and this is all in the context of the sonar equation. Remember. So now we can jump into some numbers. Numbers of examples of source levels. And I won't go through all these because you guys are probably all familiar with this, but it'll give you, a sense of what dB levels we're talking about. Tankers are, 180 in their low frequencies. Moans, fin blue whale moans are same order of magnitude, but and order in the frequency. And offshore wind turbines, for example, are all over the place. They can be really quite low, up to kind of noticeable. Navy sonars can be very loud. I won't go through that detail. There's lots of resources on that. So the one thing I should talk about is a decibel at this point, because what is a decibel? And throwing that unit around. In ocean acoustics, a decibel, sound levels are always described in terms of the decibel, and the decibel is the log of the pressure the RMS pressure of the what you're receiving relative to some reference. So it's a dimensionless number. In underwater acoustics, the reference is always 1 micropascal. Contrast, in air acoustics, they use dB, and it's referenced to 20 micropascal. So you can't compare a dB in air against a dB in water, and that's caused, that can be a source of confusion. So it just has a reference there. So I've talked about transmission loss a bit, and source levels. Now, noise level is the last term in this one, our equation, which is really important. And noise in the ocean generally is made up of the noise from the ocean, either natural or man-made noise that is coming into your receiver from away from the outside, plus the system self noise of your PAM system. And that's the noise that you receive, that you're generating inside the system. And in terms of ocean noise, well, there are lots of resources out there so you can get estimates on potential levels that you might expect in a certain area. And the Wenz curve for ocean noise is a classic. It's been around forever, and it looks something like this. I won't go through the details. This is a pretty busy plot, but basically it shows that noise levels in the ocean at low frequency are much higher than they are at high. And noise at low, and you can give you kind of decibel levels here. At low frequencies, it's dominated by shipping and earthquakes and low frequency whale calls, essentially. Seismic surveys and air guns are a huge part of this noise budget now. And I should also mention that the noise budget in the ocean has been measured to be going up as a matter of time. So these curves are a little outdated, but they still give you a pretty good estimate and a good starting point. As you go up in frequency, you can see noise is dominated by sea state, essentially. Noise coming from the surface of the ocean. Sea state 0 would be the lowest, which would be a perfectly flat ocean surface, all the way going up to, sea state 6, which is pretty rough. So that gives you, an idea of what the soundscape of ocean noise is. The other part of this total noise in the system that you're actually that you're measuring at your PAM system is the system self noise, and this is important, and you should be able to characterize this. So in general, when you're designing a PAM system, this should be less than the ocean noise level, because you want to detect signals that are, idealistically, you want to detect signals that are just above the ocean noise level. But it doesn't really need to be a whole lot further, and this is where engineering compromises come in. It takes a lot of effort and generally uses much more power to get very, very low noise level analog circuitry, for example. And if your noise level for your system is way, way down below the noise level in the ocean, well, it's just a wasted effort because you're not going to hear it anyways. You're not going to hear signals down this low because it's just going to be lost in background noise level. So again, this is where PAM trade-offs come in. So I'm going to focus just a little bit, and this is an engineering issue, on system self noise. So generally, system self noise is a combination of electrical noise and mechanical noise. And you can measure this, and every PAM system should be calibrated so you know exactly what your noise level is. So when you take a measurement and you're interpreting results, you can get a sense of what your lowest detection levels would be. And that's defined by the ocean noise level. Your self noise level should be less than the ocean noise level. And when you're making these measurements and calibration, you always include everything. When you buy a hydrophone, they always give you a noise level and they say, oh, it's way below 10 dB below sea state 0. But when you hook it up to your preamps and your A to D and put it, there's processes running around, you stick it inside of a bottle, noise gets, it adds a lot of noise. So this is an example of a noise level recorded on the system we're working on now. And these blue and red and blue curves are the Wenz curves, essentially. So this is heavy shipping noise and light shipping noise in sea state 6, state 0. The black curve is the calibration curve measured on the bench for just the electrical noise. And this is a pretty good noise curve. If someone shows you a noise curve a lot better than this, then you should be a little suspicious. And but essentially, the compromises come in at high frequency. So it's extremely difficult to get below sea state 0 above 10 kilohertz. And the good news is generally you don't really care because signals that you're interested in above 10 kilohertz are not going to be down that low. So the other half of this self noise equation is mechanical noise, and this is something you also have to calibrate out. When you add in mechanical noise, your basic calibration curve changes. And there's an example of putting this system in a nice quiet environment. Really, the only way to characterize fully a PAM system is to put it into a controlled, quiet environment. And that can be quite hard to find. Lakes are often used. So you can see here that the low frequency noise rose up probably because of, flow noise and body, slapping against the body, and there's some electrical noise that pops in. So this type of calibration can really be a part of the test out of a PAM system. So talking about noise level, we should also talk about receiver gain, which is essentially system sensitivity. And this is a very important component of any PAM system. And essentially what you want is you want to implement some type of gain in your system to amplify this tiny little signal coming out of your hydrophones to something that you can actually digitize. And generally, and this is an example of a gain curve, which I use a lot, you want a gain curve which is not flat, because you want to level out, or pre-whiten, some people call it, the noise coming from the ocean, so you don't prevent saturation. Since there's so much low frequency energy in the ocean, you want to have very little gain at the low frequencies, because you don't want the low frequency signal to wipe out the high frequency signal, basically, which you're interested in. So as you go up in frequency, you want your gain to increase. And this is a very typical gain curve. And if it mirrors, in a sense, the Wentz curves. So you want to have the inverse of the Wentz curve. So as a little bit of an aside, I don't want to dwell on this too much, but it's really interesting to think of what marine mammals do. So this is a plot of auditory thresholds for small animals, false killer whales and belugas and seals, dolphins. And it's not a coincidence that this kind of mirrors in the inverse of this gain curve that we typically implement in PAM systems. At low frequencies, their threshold for hearing, or their sensitivity, their threshold is high, which means they have very low sensitivity to low frequency noise. And but the frequencies that they care about, they have a low threshold, which is a high sensitivity. So it's kind of the inverse of the gain. So they have high gain up here and low gain down here. And that's kind of what we want in a PAM system. That's just I won't make too much of that, but that's just an interesting balance. So in summary, the sonar equation can be used to calculate detection levels, or SNR, and that can be very helpful in interpreting data that you collected. If you can make some estimates, it's only useful if you can have some sense of the transmission loss and the basic noise level that you're recording. And if you know your system sensitivity, so calibration is a very important concept. But maybe more importantly, it tells you what levels of self noise are acceptable for your application, so you can design your system and not over design it or under design it for your application. And it also can inform you where to put your SAM system to maximize your text in terms of depth and location in a particular environment. So that's going to be my brief summary of ocean acoustics, but I highly recommend a website if you want to get further into this, called docits.org, and that stands for the Discovery of Sound in the Seas, and it's run by the University of Rhode Island. Very informative website. It's a little old school, but there's tons of information. So what do PAM systems look like? And I'll give an overview of kind of current system. And the basic components of pretty much every PAM system, something like this. And this is a schematic of a system we're working on. It's actually the nose cone glider. Every PAM system has a hydrophone, and everything I've talked about here is basically single hydrophone PAM systems. Some PAM systems have multiple hydrophones. So the hydrophone is put next to the preamp, and the preamp implements all this pre-whitening and this special gain curve. It's got to be close to the hydrophone because that's where noise gets injected, electrical noise gets injected into the system. There's always a processor with some type of analog to digital conversion circuitry. The processor, which turns the voltage into a sample, a digital sample, and a processor, which can either do some type of in-situ data processing or just store it to some mass storage device. But generally, you always want to store large amounts of data. Even if you're processing it, you still want to store data. And SD cards are common storage. So you can buy 1 terabyte SD cards now. So when you stack up a few SD cards, all of a sudden you've got multiple terabytes of data storage, which is plenty for long durations. Last but not least is the power source, and in this case, it's batteries. Typically, batteries are used for most times. So I'm going to run through some examples of kind of more of configurations of deployment configurations for PAMs. And bottom moored systems are, the most common. They're the oldest and most common form of collecting data. And they look, this is an example of one. It looks a lot like what we just saw. There's a hydrophone, a bottle, a pressure housing, which contains a bunch of batteries and some electronics, and they sit on a mooring line. And the mooring line has an anchor with an acoustic release and a line of sensors with floats. A harp is a PAM system. This rainfall gauge is essentially a PAM system also. So you hit the acoustic release and it comes back. This is another example of the Cornell rock hopper system, which I'm familiar with, and it's a simpler system. There's the weights and the acoustic release, and everything's packaged into a sphere filled with a glass sphere filled with batteries and a hydrophone. So you just throw it over the side. So the pros, I'll go through the pros and cons. Moorings are great for long duration. You put them in for a year, don't see them again. You can get them into the deep water. You can deploy them anywhere you want. You can put the PAM system anywhere along the mooring line. You can get into this nice, quiet waveguide. They're stealthy because they sit on the bottom and no one knows they're there. Cons, well, they're generally, you need heavy equipment, you need ships, you need, winches and cranes. There's no real-time feedback. You don't get the data until, you recover this thing, and that could be a year later. And like every PAM system, it's limited by battery packs. You can't put, giant battery packs on these things. And batteries are the only way to really power up PAM systems. Biofouling, since you're sitting down for long periods of time, can be a problem, and often you pull the thing up and it looks like this, which can really degrade performance. So the other system, very popular, are basically what I call surface systems. So these are surface vehicles, either vehicles on the surface or drifting buoys on the surface, or a mooring with a surface expression. And the wave glider is a good example of a system like that. The PAM system on the wave glider is towed. And remember, I mentioned single hydrophone versus arrays. Well, since you're near the surface, really, you need to use an array. And so it can get quite complicated. Simpler systems is like this drifting float. You can either moor it and leave a surface expression, or you can just let it drift. Commercial units you can buy. Pros, power is not an issue generally because you have solar. That's the biggest advantage. You can run it forever. And you can communicate with it. Good positioning through GPS. You can, if you're close to it, connect with Wi-Fi, and you can definitely do Iridium as much as you want. So you can get real-time feedback on data. Power, with lots of power, with good communication, is a perfect scenario for doing detections in situ. They're easy to deploy. Basically, just throw them off the side of a ship, let them go. Cons, you're in the surface zone, which is not the ideal place to make PAM measurements. Because of that, they often require complex arrays and code arrays, and they're not stealthy at all. So the other type of system, which I would classify as generally in use, are called I would call them subsurface systems, and these are gliders and floats. Becoming more popular. And here's a couple of examples of one, a sea glider with a hydrophone on the back. This is an Apex float. These are all buoyancy control devices. There's an Apex float with a PAM system in it that floats around. Pros, flexible spatial sampling. What I mean by that is you can go up and down in the water column, and you can choose where you want to make your acoustic measure. Generally, you want to make it lower and deeper in the middle of the waveguide. Because of this, you often get very good acoustic data. There's near real-time feedback because all of these devices have to come up to the surface occasionally, and then you can talk Iridium. So you can come up every week or every day or every month or something like that. They're really easy to deploy and recover. And they're stealthy because they're below the sea surface. Cons, well, they're relatively expensive compared to the others. Surface vehicles are not cheap, but these are operationally expensive sometimes. And they're relatively complex in terms of how you operate them. PAM integration can be complex. And this is an example of a sea glider kind of splayed out with a PAM system put into its instrument package area and a hydrophone strapped on the back. You see that a lot when you're working with gliders. You don't want to be doing that on the deck of a ship. But gliders are great. And here's an example, and this is data from a glider that's flying here off the coast of Massachusetts. And this is just from, I just a screenshot I took a few days ago. So it's data from last month. And it's a Slocum glider with a PAM system and a detection system running on it. And it's running these grid lines and coming to the surface and reporting sightings. And in this case, it's right whales and fin whales. Probably most of these are fin whales, but some of these are right whales. So it doesn't give you the exact location of the whale. It's just the location of the glider when it heard the whale. So the whale's in the general vicinity, and use the sonar equation to back out the location if possible. So it's a really good example of gliders and how useful they can be. So you can always combine systems. And this is an example of a system done on the West Coast. I'm not sure exactly what it was supposed to, some wave energy projects where they combined quantum mode PAM systems with surface expressions and acoustic links between them. Pros, the only reason you do this is if you want real-time feedback. Cons, they definitely get complex. So that's kind of a summary of what's out there. Where should we go? Where do we want to go? Looking ahead in terms of system design, well, I just take the best from the above. So an ideal system would be low noise, below C state 0, have long duration, which means low power, your PAM system, because power system has to power the platform and your sensors. And if the PAM sensor is sucking power, you're just going to, kill your duration. A number that I like to use just over time and experience has just been like PAM system can draw 150 milliwatts when it's running, then it can fit into a lot of platforms and a lot of standard battery size battery packs and last long enough. It's pretty low, but it's an ambitious number. So you want systems to be easy to deploy and recover and provide flexible sampling strategies. So these are all just kind of the best from these systems above. And an ideal system, in my mind, would be a fully integrated platform and sensor solution. So you can buy PAM systems now, and people have platforms like gliders, and they do the integration themselves. Well, that generally takes a lot of effort and a lot of upfront engineering costs, and there's a lot of risk associated with that. So an ideal system would be a platform integrated a sensor integrated into a platform from the get-go. And this maximizes data quality, essentially. You can address self-noise issues from the start when you're designing a system. Looking ahead in terms of real-time feedback, which is something everyone wants. We always want lots of raw data, but we also want to get the data back in real time, or some filtered version of the data, either detections or spectrograms or something like that, so we can make decisions on the fly. And this is all dependent on in-situ data processing. This has already happened, and I showed you, lots of people are working on this. And I showed you an example of Whale Map, which comes out of a program called Robots for Whales, an ONR-funded program. Very successful. But we need to move this from demonstration, because there's only a couple of gliders out there, right? Into real operations where you want to put hundreds of gliders into an area, for example, or hundreds of floats. The holy grail for in-situ real-time data processing is high-level machine learning. There's been leaps and bounds in this area. We haven't quite been able to implement these onto a low-power system. So this little schematic gives an example of what you ideally want. Want to provide high-level tools like TensorFlow. People want to work in Python. They want to train their machine learning models, on their laptop, and then port them to a low-power embedded system. And this is an example of putting TensorFlow on an Arduino, this is the type of processor generally that you're using in a PAM system, Cortex M4, something like that. So you want to provide results instead of raw data. Scientists will always want to have the raw data, and as an engineer, you always want to have raw data. But you don't necessarily want to sift through it. sift through 10 terabytes of data. You want to provide results to the user in real time so they can make decisions. Offshore development for wind farms. You want to make sure animals are not in the area. You can't wait a month and find out that there were animals in the area. You need the information back within hours. And also results for autonomous vehicle control. So results that go to the vehicle so the vehicle can make decisions. And this is looking ahead. This is an ideal system. So the vehicle can do adaptive sampling, move up and down the water column to find the place where you're best getting the best detection levels for tracking targets, localizing targets. So that's about it. So I'm going to kind of conclude there, and we'll take some questions if anyone's interested. And I talked about, so just in summary again, I threw the sonar equation out there, talked some basics physics of the ocean, give examples of existing systems, and what I think of an ideal system would look like. So thanks.
Great. Thank you so much, Chris. We have had a couple questions come in just while you were presenting, so I'll start with those. But in the meantime, feel free to either, like I said, raise your hand or pop another question in the chat.
Should I stop sharing, Frida?
Sure. Now we can see your face. So first question from Donglai Gong. He asks if the source is placed outside the SOFAR channel, would sound enter it and get trapped, or simply would not enter it? For example, in a shallow source.
Yeah, it definitely couples into the sound channel. It's better if it's in the sound channel because the coupling works in the other way. Sound gets kept out of the sound channel, but generally sound, and it's a good point because you can hear ships right in the sound channel. So the surface noise is getting coupled into the sound channel and then transmitting with low transmission loss. So yes, for sure. And also earthquakes. I mean, earthquakes are a good example. People track seafloor earthquakes all around the world with really long distances, and the only reason you can do that is because the SOFAR channel, something called T phase, and basically the sound from the seafloor gets coupled into the water column.
Thank you. We have another question from Christian Meinig, and he asked, and this might be something if you have the data. Yes, could you overlay some self noise from traditional PAM systems such as Sea Glider, Slocum, and Wave Glider?
Well, I can only no, I don't have that slide. I can it's a good one. I have to you don't often get self noise system for lots of other PAM systems. So the only self noise systems that I really have systems that I've built. The one that I showed is for a glider. But yeah, I'm sorry, I'm just not prepared to show data like that. I guess the real question there is which types of systems have higher self noise? Is that the essence of your question, Chris?
Yeah, Chris, just thinking of, we looked at the Wentz diagram, and so often, there's multiple levels of self noise, and knowing roughly what sea state level those are comparable to, and basically to address the gaps.
Yeah.
To understand, okay, we're currently here at self noise for a lot of the systems. Obviously, Heffring and you are developing this new glider, so you must have had some goals of trying to close gaps. So are we roughly, what dB level are we at self noise now, and how do we make better vehicles in the future to avoid that?
Well, I showed that plot, which is essentially the self noise for the system that's going in the Heffring glider. And I don't know if I can pull that back. I'd have to start sharing again. Should I do that?
Yeah, that's fine. Go for it.
How do I get back that far in the presentation? Sorry, I'm not. Let me share this one. I'm gonna have to probably stop presenting for a second. Oh, here we go. Go all the way back. No, I don't want to do that.
Okay, we'll just take us a few seconds.
Yeah. Okay. Here we go. In reverse. Yeah. Really fast.
We'll see if we missed anything.
Yeah.
Maybe more questions might come up.
Yeah. Okay. Here we go. We're getting there. So this was the total self noise for the particular system we're talking about. And you can see we're below C state 0 up until about 10 kilohertz. That's a typical kind of self noise curve that you'd shoot for. I'm sure what you mean by the gaps. What do you mean by the gaps, Chris?
Right. Your self noise there. That's when you say electrical mechanical. That includes the glider.
Yeah.
Electromechanical set screw. Or are you just looking at electronic self noise from your?
Oh, well, that's a really good point. So, in a glider, there's lots of mechanical noise. And you generally won't be sampling acoustic data when, for example, the motors that are controlling the buoyancy engine are on, because you're not going to hear anything except. And you're not going to sample when it's on the surface because it's splashing around the surface. Again, this is a vehicle sensor integration issue. So in every glider system that I put a PAM system on, we always get status updates and talk back and forth to the glider controller. And so the PAM system knows when to record, when it's quiet, not. So you kind of record when it's on its nice, quiet descent and ascent. You don't record on inflection. So, I mean, hopefully that's kind of what you get at. And that's true with any sensor.
Yeah, that's it. But some of the, I've seen plenty of data sets where that's not done. Systems that you weren't designed and plenty of wave gliders. So community-wide, right? Those are the gaps I'm talking about. How do we advance that system integration from any vehicle technique, right? That's the community-wide gap, not necessarily your particular system.
And I understand exactly what you're talking about. Yeah. So you address that by having the communication between your PAM system and your platform. So the PAM system really needs to know what's going on with your platform. And in the wave glider, well, that's a whole special case. There's a lot going on with those guys. But again, often people will just kind of, tie wrap a PAM system onto a vehicle and it's just recording all the time. And if you come back with, multiple terabytes of data, it becomes a real hassle sifting through that data and finding out where the good data is and where the bad data and what's real data and what's noise. So I think that's what you're talking about. And that's all about having a PAM system integrated in with communication between the platform and the sensor.
You're exactly on my point. So the idea there is if we get this integration right, then we can harness machine learning tools so that we have standardized data sets. I don't think the community is yet on standardized PAM data sets, so we can develop those ML systems for detection in a community-wide ways. Right now I see each bespoke science group doing it on their own, and we haven't harnessed any standards yet.
Absolutely. And that's why I think it's important to have people developing integrated platform sensors from the get-go. There's always going to be researchers that have a platform and they have a PAM system and they want to do the integration themselves, and that's fine. But if you're doing any type of machine learning, you need to have some metadata associated with your acoustic data, so you're not trying to figure out whether the motor's on or not. Good question. Very good question.
I think we have an anonymous question that's come in.
We do. Yeah, I have a question here for Chris. What is the criteria to choose the best hydrophone for autonomous? Sorry, everything moved. What is the best criteria?
Unshared.
No, we're good. What is the best criteria to choose the best hydrophone for autonomous PAM platform such as a glider? So your selection criteria for the hydrophone.
Best criteria is get the most expensive hydrophone you can afford, essentially. I mean, don't go cheap. Hydrophones are they're an art form. There's companies out there that make them. HTI is what I use all the time. When you buy their high-end hydrophone, it can cost you $1,000 or $1,500. But you go and buy a $100 hydrophone. You're just going to be trying to reinvent the wheel, and these guys are really good at making low noise hydrophones. So criteria is base noise levels, and they'll define that either in terms of sea state often do. They'll say it's a sea state 0 hydrophone. And if you ask any hydrophone manufacturer that can't give you a plot of their noise levels across the bandwidth of the hydrophone, then you probably don't want to trust them. So they will give you those numbers. But again, it's not just a hydrophone. You always want to get the best hydrophone possible. But most of the noise comes from your electronics, your preamps and your A to D. So it's a tough one. Yeah. Hope that answered your question, Chris. A lot of questions from Chris. Any other Chris?
Yep. Well, we've got another one from Donglai, but this is the same Donglai, not a different Donglai. What do you think about using PAM for multi-platform operations for the localization of acoustic sources like marine mammals? Thoughts about accurate and low energy clocks for use on moored or gliding platforms?
Right. That's a big application, right? People definitely do that with moored systems. So you're recording sound and you have to have a very accurate clock. Generally for localization, you don't need microsecond accuracy. You need millisecond accuracy because you're not trying to locate these things within meters. And you don't really know the exact position of where you're mooring it anyway, within 10, 20 meters. So in terms of clocks, well, there's been a lot of progress. You used to have to put these crazy, clocks in systems that were really expensive. Now you can buy, chips that have temperature compensated real-time clocks in them, MEMS devices that are kind of bordering on accurate enough. They still drift over time. Moorings, it's a real problem. And a lot of effort's been put into. I don't have any kind of names of particular clock manufacturers off the top of my head. I used to know that stuff, but I haven't really dealt with that issue in a while. On platforms such as gliders and floats, timing is GPS timing. So when you come to the surface, you basically resync your PAM system, and you can resync to a GPS. Every GPS system gives a PPS signal, which is a pulse per second signal, and you can interrupt your PAM system and timestamp your PAM data on that system. And generally, you can get millisecond type accuracies you need for localization. Again, biggest problem probably is not knowing the exact location of the location and coordinates of your PAM system as opposed to the timing of your system. Some people, they'll drop a mooring and they'll navigate in the mooring very tightly. People that do seismic, like for example, nuclear test ban verification, the whole network, very low frequency PAM systems out there that have atomic clocks on them, and they run and they know the very precise location of the moorings in the hydrophone, so they can do localization of earthquakes quite precisely. It's been done for a while on moving platforms. GPS.
Thanks, Chris.
We have a question.
We have another question from Natalia Lace. She asks, this is a kind of an exciting question if you have stories about it. Did you have any instances of sharks attacking gliders, damaging them or taking them out completely? For example, in Hawaii, a shark chewed on the hydrophone and damaged the entire system.
Take some pictures of that. Yeah, I mean, animals. I mean, especially gliders. I've heard lots of. I don't operate gliders. I build systems, and then the glider goes off, and I never deal with it. So I think that people that operate gliders have lots of stories like that. Basically, you put something in the ocean, it's going to get beat up in every way possible. So I don't have any real horror stories to tell in that regard. Sorry.
If we encounter any during any of our Heffring testing, we'll be sure to put it on our social media channels. You can count on that.
Right. Generally, sharks and animals don't touch systems on moorings or sitting on the seafloor. It's when they're flying through the water column. Problem. Most of the problems are not sharks. They're fishermen or other people that are just kind of curious what's that mooring doing there? What's this glider? We were just talking to a guy here out of Gloucester the other day, maybe not the other day, a week or so ago. He was just out there and he saw a sea glider sitting on the surface. So he just picked it up and pulled it in his boat and brought it to shore. And it turns out the sea glider was just doing its operation, but it was on the surface, calling home. So, and I can't remember who owned the sea glider, but, yeah, that type of stuff happens all the time. So.
We have another question from Francois Javier. Thanks for your presentation. Do you think that a cooperation between fixed recorders and moved recorders on board gliders or UUV or USVs is possible to extend the range of detection in an area of interest?
Yes, and definitely people are working on this type of stuff. The Navy has spent lots of research money on swarms of gliders, talking to fixed systems through underwater modems, acoustic modems. I personally think we're at a junction now where the technology is, in situ detection. The costs are low and the capabilities are high now, where we can start doing really complicated things like that. So yes, it's not something you're going to buy and do, tomorrow. But I say within the next, within 10 years, we'll see that type of stuff. Very complex systems running around there. No reason not to believe that. Plenty of problems to solve.
For sure. Well, it looks like that's all the questions I see. Chris, did you have any other questions that came in directly to you? No? Okay, great. Well, I guess we can conclude there. Please, but there will be a survey that pops up as soon as you leave the meeting. If you please fill that out. It's really short. We would appreciate your feedback for future meetings and presentations. And we will be presenting another webinar in about a month's time on glider operations. So if you found us via LinkedIn or other social media, please follow our channels so that you can make sure to get an announcement about that when we present it. Thanks again, everybody, for joining, and have a great day.
Thanks a lot.
Thanks, Chris.